Ladies and gentlemen, boys and girls, welcome to another lesson of Transparent Physics. In this lesson, we're going to be wrapping up the Newton's Three Laws Motion Trilogy with a discussion of the third one. And as the GIF/GIF at the bottom of the slide suggests, it's easy to confuse how this one actually works. So let's spend some time talking about it so we don't get confused as well. Okay, by the end of this lesson, you should be able to describe Newton's third law of motion, which is not an easy task in and of itself. There is a way to write the forces involved in Newton's third law to help you keep them organized, and we're going to talk about how that notation works. And then we're going to talk about an area that introductory physics students often get confused on in terms of the difference between action-reaction forces and balanced forces. Just as with the first and second laws of motion, the third law of motion can be written a couple different ways. We'll start off with a very formalistic and probably intimidating definition, but we'll break it down. When object A exerts a force on object B, the force that A exerts on B is simultaneously matched by a force that B exerts on A. These forces are equal in magnitude and opposite in direction. The idea of what this is saying is, hey, we've got two objects and they interact. Maybe it's a push, maybe it's a pull. However that occurs, when one object exerts a force on a second object, the second object automatically exerts a force back on it. The forces are the same size, but opposite in directions. If you push to the right on a wall with a force of 50 newtons, the wall pushes back on you with a force of 50 newtons in the opposite direction. Sometimes this law goes by the nickname the law of interaction because it tells you how any physical interaction in the universe has to occur. There has to be this action-reaction force pair, as we say it. And you simply cannot interact with an object without it interacting back with you. And this is a source of confusion in some cases because it's not always immediately obvious that the forces are interacting with each other, say for, like the moon and the earth. It seems obvious that the earth is pulling on the moon, but Newton's third law says that the moon also has to be pulling back up on the earth. But we'll talk about an example or two of that as we move through this lesson. Now, the previous formulation of Newton's third law, it's a pretty technical one, I know, and probably not even the one that you're used to, I'll have to admit. There's another way to write it, which I call the Casual Friday version, and we will explore it through the eyes of one of America's greatest treasures, Garfield the cat. And so in this Garfield cartoon, Garfield is startled by Odie. Garfield makes the statement, for every action there is an equal and opposite reaction, and then he clobbers Odie into his own food. And that expression, for every action there's an equal and opposite reaction, is an expression of Newton's third law. I caution students to use this because when you're saying it that way, you're basically using it in the Garfield context, where it is almost a discussion of like karma or the consequence of your actions, like some sort of balancing of the universe. I don't know, it gets way out of line with what Newton's third law is really actually about, because the fact that Garfield is slamming Odie into his food is not actually, according to physics, the action-reaction that goes along with Garfield's face going into his food. These are separate events. So to be a little more technical about it, I encourage students, if they want to use this one, and again, it's go with what you know, but let's try to tighten it up. I like to add the word force in two locations. So this puts the emphasis on the idea that Newton's third law is about forces. So for every action force, there is an equal and opposite reaction force. And that, I think, tightens it up enough to make it a lot more functional in the context of an introductory physics class and tries to take it away from this sort of cosmic destiny sort of idea that is sometimes associated with it. Newton's third law can also be expressed as sort of an equation shorthand. And who's coming on the screen? We got those vector notations, right? The vector notations means we have to watch out for a measurement that has both a magnitude and a direction. So if we take a look, a standard way of writing Newton's third law, it might look like the force on A by B is equal to and opposite the force on B by A. Visualized a little more clearly, we can imagine that we have a bulldozer that is interacting with a block, and A for the bulldozer, B for the block. So the A bulldozer is pushing on the block, and if you notice the way I draw it, the dot is on the block. The dot is on the object where the force is acting on. That also helps you keep them straight when you're sort of drawing these out. So there is a force on the block being pushed to the right by A, and as a result of that interaction, immediately and simultaneously, there is a force back on the bulldozer from B. So there's a force on A by B and a force on B by A. And we can often summarize that once we're comfortable with the notation. You don't have to write the ons and bys anymore. The on term is the first term and the by term is the second term. And as I noted, this is often a shorthand way of writing Newton's third law. And sometimes it's even used in a problem. Sometimes you sort of make a statement saying, hey, this force is equal to the other one for this reason. And I think the subscripts are really important because it really keeps you focused on the fact that there are two objects interacting there. And remember, the standard is we focus first on the object where the force is acting on, and then we discuss who's creating that force. In learning Newton's third law, I find there often is some confusion because the idea of a set of action-reaction forces that come along with that interaction for Newton's third law looks an awful lot like something we've talked about before, which is balanced forces with the first law. And it's pretty easy to get those two things confused with each other. At first blush, they do look very similar, so let's investigate this a little further. And seeing this guy balance the can of soda on the glass makes me kind of thirsty, so I'm going to take my obligatory tea break right now. That's good. So let's investigate. We're going to take a still shot of the can balancing on the drinking glass, and we could look at it from this perspective. We could say, hey, there is a force acting up on the can from the glass. There is a force acting down on the can from gravity. And the internet tells me that the weight of a full can of soda is around 3.8 newtons. So you can feel good about this video, that it is scientifically accurate. Now we can take a look on the other side of the slide. In a very similar situation, we've got a force acting up on the can from the drinking glass and a force acting down on the glass from the can. Again, there's one force up, one force down. They're the same in magnitude as each other on each side. Opposite directions, just like the opposite side does have as well. So these, again, look very, very similar to each other. One of these is an example of Newton's first law, and one of these is an example of Newton's third law. So the one on the left is Newton's first law. The argument here is that these are balanced forces. When you take a look at the force acting up and the force acting down, they are balanced because the net force adds to zero. The can is not going to be accelerating. If it's at rest, it will stay at rest. And a giveaway for this scenario is that the forces have to act on the same object. Forces can't balance each other out if they're acting on different objects. So they're both acting on the can of soda. That's indicated sort of graphically by the fact that when I draw my forces, there's only going to be one dot with both forces coming off that dot. The fact that there's only one dot means there's only one object that I'm interested in as far as the forces that are acting on it. On the other side, we've got Newton's third law. Newton's third law is action-reaction force pair. That's object A interacts with object B. In this scenario, object A we can consider to be the can. Object B we can consider to be the glass. The glass exerts a force up on the can exerts a force down on the glass. Again, they are equal in magnitude and opposite in direction. Now, these two forces don't balance each other out. Even though they are equal and opposite, just like a pair of balanced forces would be, they act on different objects. So if the forces act on different objects, they can't cancel each other out, because only forces that act on the same object can work to canceling each other out. And so these would be considered equal and opposite interactions, and the giveaway there is that the forces act on different objects. So again, there's a lot more practice to this, but just be cautious both when setting up your own information or looking at someone else's. In the first law scenario, you know that the acceleration has to be zero because the forces are balanced. In the third law scenario, the acceleration might be zero, it might not be zero. Any interaction has to be governed by Newton's third law. So Newton's third law, the forces associated with it can just as easily result in acceleration as in not acceleration. And we'll wrap up with one final example. And so we've got a studio wrestler, we'll call the one gentleman Black Speedo. So Black Speedo exerts a force on pink leggings and takes pink leggings down to the mat. If we look at a screenshot of the interaction, we can see that there is a force acting to the right. There is a force acting on pink leggings from Black Speedo, and there's a force on Black Speedo from pink leggings. These forces are equal in magnitude and opposite in directions. So when we take a look at the nomenclature for that, we would say the force on black by pink and the force on pink by black. And I'm not going to hazard to guess what the magnitude of that force is, but whatever it is, it's the same amount of force on both objects. Now I will say that, and people will look at the video and they'll say, well, transparent physics. Doesn't pink have way more force acting on him? Because look, he gets thrown backwards. And there's more to what happens to an object than just the fact that the forces are equal. And the key thing here is to recognize that Newton's third law only guarantees the same amount of force. It doesn't guarantee the same effects of that force. In order to know what happens as a result of an unbalanced force acting on you, we need to then appeal to first and second laws of motion, because the acceleration is dependent on both the amount of unbalanced force and the object's mass. So I'm going to argue, and it's hard to tell from this video, but I feel that the gentleman in the Black Speedo is more massive than the gentleman in the pink leggings. He just looks a little bigger. So that's one thing right there, even though they have identical forces acting on them, because pink leggings is less massive, he's going to have a larger acceleration. And if you look at Black Speedo, it is my opinion that he does slow down on impact. He's moving forward at a certain pace, and on impact he is still moving forward, but he almost seems to hover in the air as he slows down. That is the result of the force acting back on him. So he is pushed to the left just with the exact same amount of force as pink leggings is pushed to the right. But their masses make the effect of that may be different. And in addition, when we look at Black Speedo, we could measure his initial speed and then check his final speed, and they would both be moving in the same direction, but his final speed would be slower than his initial speed. The guy in the pink leggings also has an acceleration, but he's starting slower on impact. He's almost at rest when he gets hit, and then he gets thrown backwards. So he does have a change in velocity as well. Maybe even if they were the same mass, they would have the same change in velocity, but the idea is that maybe it's more dramatic to our eye when an object slows down, stops, and gets thrown in the opposite direction than it is just to be slowed down in the direction you were going in. So again, a lot of things can come into play when we visually try to interpret the interaction of two objects. Don't read too much into it beyond Newton's third law saying that the forces of interaction must be equal in magnitude and opposite in directions. Everything else that happens, we're going to have to appeal to other laws to figure that out. Okay, longtime fans of transparent physics may remember from the previous video that Newton's first and second laws, in my opinion, maybe we have one too many laws there. We talked about the idea that if we had to, we could probably eliminate the first law, because realistically speaking, the second law has the formula F net equals ma. So it tells us what happens when the forces are imbalanced. We get an acceleration, but as a bonus sort of subfact, if we set the net force equal to 0, then there's no acceleration. So the first law is already tucked into F equals ma, which is the second law. So maybe we don't need the first law after all. In addition, I'm going to continue on that trajectory, continuing my extreme makeover of Newton's 3 laws of motion. And I'm going to argue that Newton's third law of motion really isn't about motion at all. It's about the interaction of two objects. Now, maybe that results in motion, maybe it doesn't. Maybe it results in motion, but it's constant velocity. Maybe it results in motion and there's acceleration. Maybe the objects are at rest and they stay at rest. But it's not a guarantee that it's about motion. It is, again, it's the forces that arise when two objects interact with each other. And I think that's a pretty important concept. And in fact, when you take a look at Newton's laws of motion, they're really kind of laws of forces, not laws of motion. And so if I was going to redo them, I might write the third law as the new first law, because it tells us where forces come from. And once we have forces in play, then we can tie it into Newton's second law, where it talks about the impact of those forces on objects, depending on whether they're balanced or unbalanced. So you heard it here first. I'm not saying it's going to go viral, but Newton's 2 laws of forces, the first law being the law of interaction, the second law being the law of acceleration, or maybe not acceleration. I have to work on the names a little bit, but you get the idea. And if you found the content useful, please help the channel grow by liking, commenting on, or subscribing to this channel. And as always, I appreciate your time. I hope I've helped make things a little clearer for you on this lesson of transparent physics.